So last time I told about sampling methods, so different methods of taking the samples from populations, and namely that was the simple random sampling, systematic random sampling, stratified random sampling, and different subtypes of stratified sampling like clustered random sampling. And we've seen that the samples themselves may be different, not only the methods, but even when using only one method, you can draw several different samples. They may overlap a bit, or they may be totally different. But what happens if we take all the possible samples? So here we have a population of 8 entries, and listed under is the list of all the possible samples of size 2, right? So you can draw 28 different samples of size 2 from the population of size 8, and you can calculate that using the combination formula. I guess you all remember the combination formula. So number of combinations of 2 out of 8 is well, (28). Okay, so some of our elements, some of entries in the population are the same. For example, we have 4 entries of 2, 4 copies, so to speak. So some of our samples will also be the same. For example, we have 6 different samples of size 2, which consist of 2 entries of 2. Or we have 4 different samples which consists of 2 and 4. So you can so you take 4 and you can have either this 2 or these 2 or this or this, and that gives you 4 different samples. So here I listed all the samples with a number of copies where appropriate. So the sample consisting of 2 2's repeats itself 6 times. The sample, any sample which contains only 1 2, repeats itself 4 times, and so on. And then here in the second column I've calculated the mean values of our samples. By the way, true mean of the population itself is 8.25, and let me write it down here. Okay, and you can see that sample means, some of them are kind of close to 8.25, for example this one, or even this one with some approximation, and some of them are really far away, like 2 or 23. Okay, but now I want to do something different. Let's treat these mean values, so sample means, as a new random variable. So you draw entries into your sample in a random way, so your sample mean is also random, and for each random variable we can find the distribution. So in this case it's discrete, so instead of a frequency distribution I can just use frequency table, and you can see that table here. So I've put each entry, each sample mean, so let me denote it as this. It's a sample mean, and here is the frequency for that sample mean, and I'll mark it as f of sample mean. Okay, and now let's try to graph the distribution. Here on the upper panel, so here I have graphed the distribution of the population itself. We have 4 entries of 2 here, we have one entry of 4, it's here, one entry of 8, and so on. And now I'll do the same for the sample means. So we have 6 entries of 2. Oh, and by the way, let me make the brush a bit larger. So 6 entries of 2. 1, 2, 3, 4, 5, and 6. And then we have 4 entries of 3. So 1, 2, 3, 4. And we have 4 entries of 5. So 5 is here, 1, 2, 3, and 4. 1 entry of 6. 4 entries of 9. So yeah, so this is 2, this is 4, this is 8, and so on. So 9 is here, and we have 4 entries for that. 1, 2, 3, 4, and 1 entry for 10, 1 entry for 12, 4 entries for 16. 1 entry for 17, 1 entry for 19, and 1 entry for 23. So that's the distribution of sample means, or the other name for that is sampling distribution. So this is the distribution of population and this is the distribution of sampling means. Or as we already said, it's also called sampling distribution. So one more time, this one on the top panel is the distribution of our random values themselves. So distribution of x. And this here is the distribution of sample means, of different sample means for samples of size 2. So I'll put n equals 2 here. Okay, so we can notice a couple of things. First, our distribution, the sampling distribution, is more condensed than the distribution of a population itself. The range is smaller. So for population it's this one, and it's 28, 30 minus 2, and for the sampling distribution it's, okay, I'll put it right here, it's this one, and it's equal to, so 23 minus 2, it's 21, it's smaller. And there is a thing, when you increase the sample size, so if you take, for example, samples of size 3, oh, and let me think a bit, maybe we will do that. So how many samples of size 3 can we have? Number of combinations of 3 out of 8 is 8 factorial, 5 factorial, 3 factorial, and that's 8 times 7 times 6 divided by 6. Okay, that's 56. There is no way I will sit here and list all of the 56 copies, samples. Yeah, but some of them will repeat each other. Okay, so let's do that. What can go wrong, right? I will rewrite the population here because I don't want to go back all the way. And in fact, I will pause the video here. I'll pause the recording. I'll put the population. I'll put all the samples here. And then I'll come back to you. So, it's ready. I did what I said. I have listed all the samples of size 3. So, if you want, you can pause the video at this frame and check everything. So we have 1, so 1 and 6 here, 7 samples of 4 copies each, and then we have 4 samples of 6 copies each and 4 samples of 1 copy each. Okay, so in total there is 56 samples, as I already said, and I calculated the mean values, sample means, and then I went ahead and made a histogram, so distribution and the histogram. And as here it's not discrete anymore, well, in fact it's discrete in a slightly complicated way, but it would be easier for us to treat it as a continuous random variable, and so I made the frequency distribution instead of a frequency table. And I draw the histogram of the distribution. So the red histogram is for sample size 3. And then in green, I made a histogram for sample size of 2. And you can see the difference. So we've seen that sampling distribution covers less range than the data itself, so it's more concentrated. And now we see that as we increase the sample size, as we move from 2 to 3, it concentrates even more, so it becomes more clustered. And it clusters towards a special point. So we have a point here, somewhere here, which is our population mean, 8.3. Oh, 8.25, sorry. So that's our population mean, and you can see that the maximum, the peak of the distribution is moving towards the population mean, and so do the boundaries. They are also moving towards the population mean. So as you increase the sample size, your sample means become more and more concentrated around the true population mean. And also, if you calculate the mean of all the sample means, then you will get the true population mean. So it would be easier to check that here. So you have the frequency table, you can calculate the mean, and you will get 8.25, which is the population mean. Okay, so that's the common rule. No matter what is the initial data distribution, your sampling distribution will always be concentrated around the population mean, and moreover, the larger samples you draw, the more close will it become to a normal distribution. So here, several general examples. You can have populations which are distributed in different ways. So our case, the distribution we looked at, is more close to this one, to the fourth one. But we can also take the uniform distribution or any other kind of distribution. And as we draw the samples and look at the sampling means, sampling distributions, we will see that they tend toward normal distribution. So here you can see what will the sampling distributions look like for different sample sizes for different starting distributions. And in the end, you can see that for a sample size of 30, it's almost ideal normal distribution. Well, my drawing is not perfect, so you might of course say, hey, this one is not a normal distribution, it's some strange crooked thing, but in truth it is normal distribution. It is almost normal distribution, and it's only my drawing that makes it look weird. Okay, so that's the law, that's the rule. Whenever you take a large enough distribution and you start sampling it, so you take all the possible samples of the same size and you look at the distribution of sample means, then for larger sample sizes, that distribution will tend towards normal distribution. So in the end, you will get the normal distribution. And the sample size of 30 is almost always enough to get a normal distribution. Well, almost normal distribution. That's called central limit theorem. So let me put it here. So central limit theorem. And whenever you hear that term, the central limit theorem, first thing that comes into your mind should be that the sampling distribution for a large sample sizes tends towards normal distribution. A mean of that normal distribution will always be equal to your population mean. So in our case, when we finally get to the normal distribution, mean of that normal distribution would be 8.25. In fact, that's not true, because our distribution, our data is too small. It's only 8, size 8. So there's no way to make a sample of size 30 from that data. But if we had instead a data consisting of 100 entries or 200 or 1,000 entries and so on, and if we drew the samples, all the possible samples of size 30, then we would have the normal distribution as the sample distribution. Okay, so that's about the central limit theorem. And now that central limit theorem tells us something which we can use for our own good. So let's say you want to estimate the population mean, but you don't want to deal with the whole population. So I'll go forth and put a crude imperfect graph of the normal distribution here. So population mean is here, but when you draw the sample, your sample mean won't be equal to this one. So as we can see here, for example, we have all kinds of sample means, and none of them is exactly 8.25. Some of them are close, some of them are not, but whatever. So most probably your sample mean, I'll call it X bar as always, will fall somewhere around, for example, here. Yeah, maybe. So that's your, by the way, let me use a different color for our sample mean so you won't mess them up. Okay, so this is our sample mean and this is our population mean, and the distribution on the graph is the sampling distribution. So it's not the data itself, it's sampling distribution. Each value on the x-axis is some value of sampling mean. Okay, so now we have this sampling mean. We know that it's not equal to the true mean. Is there any way that we can at least know how much of an error we are doing? And the answer to that question is yes. So we can have two different cases. So one of them is when we know the standard deviation of our initial data, maybe from prior studies or maybe from some other place, but let's just imagine that we know the standard deviation of our data. Knowing the standard deviation of data, we can find the standard deviation for this distribution. I'll put it like this, and I'll mark it as sigma of x bar. Well, in fact, it's not exactly this one, it should be lower and so on, but whatever. We know that our standard deviation measures the spread, and so this arrow also measures the spread in some way and so on. So just to illustrate, I put that arrow. So we have our population standard deviation. So I'll put it as pop std, and we know the standard deviation of sampling distribution. We want to know the standard deviation of sampling distribution. So what we will do is we take our population standard deviation and we divide it by square root of a sample size. So if your samples are of size 2, then you put 2 instead of n. If you have a samples of size 30, then your n is 30, and so on. Okay, and now you might want to remember one thing. So we used a thing called the z-score when we were dealing with normal distribution, and that score was our value minus mean value divided by standard deviation. So in this case it would be x bar minus our true mean divided by standard deviation of the sampling distribution, right? And now you know that you can calculate this area, or you can calculate the probability of your random variable being in this area, and that probability depends only on our z. So you take your z table, you look at the desired value of z, and then you get your probability. So just for example, if your z is 1.96, then your probability is 95% approximately. Not exactly, but it's close to 95%. Okay, so now we are going to turn that thing upside down. So I know my, what do you call it? Sample mean, x bar. And I want to find the population mean. Well, at least I want to know how far I am from population mean. So what you do is you choose some probability first. So for example, you want to be 95% sure that you are close to the population mean. Then you go to the z table, you find the appropriate probability, you find your z value, and it would be 1.96, and then you say so I'll take an interval x minus z times this thing and x bar, and x bar plus z times this thing. So we can calculate our standard deviation for sampling distribution. We find the z table from we find the value of z from the z table based on the probability that we choose ourselves. We have already calculated our x bar. So we can find those boundaries, and then we can say I am p% sure that the true population mean lies inside those boundaries. So just as an example, if I want to be 95% sure, I will use x plus and minus 1.96 standard deviation of the data divided by square root of sample size. So again, if you want, you can go back to our initial example data, calculate the standard deviation, then use any of those samples of size 2 and do this thing. But there your results will not be very good because your sampling distribution is still not normal distribution, and it's enough to look at the graph to see that it's not a normal distribution, it's not a bell curve. Okay, but if you take the large data set and you take a large sample from that data set, maybe a sample of size 30 or 40 or 50, and then you do all of these things, you will get your interval in which the population mean has to lie. So looking at the Z table, you can also notice that when you take larger values of Z, then your probability becomes higher. So if you want to be more sure in your interval, then you need to make that interval more wide. And if you need more tight intervals, then you have to accept that your probability will be very low. So you can do something like x plus or minus 0.01 sigma over square root of n. And then your p would be very small. I don't know even how small it will be. Maybe somewhere around 1%, or maybe 0.1% or 0.01%. So it's as good as saying I don't know, right? And if you want to say I know with any level of confidence, then you need to choose wider intervals. So by the way, this thing is also called the level of confidence. I'm 95% confident that true population mean lies inside this interval. And the interval itself is called confidence interval. So let me put it here again as a neat formula. So I'm p% sure that my population mean lies inside the interval, which is x minus z sigma over square root of n, and x plus z sigma over square root of n. And this interval here is called confidence interval. So it's confidence interval. A confidence interval of significance p. So this one is a confidence interval of 95% significance, or 95% confidence interval. So you can say confidence or you can say significance. Okay, so that's your confidence interval for known standard deviation, population standard deviation. And you may ask, well, what I do if I don't know the population standard deviation. And I'll say, well, you can calculate your sample standard deviation. So you have your sample, it's only one sample, you have calculated the sample mean, and then you calculate the sample standard deviation, and then you use the formula that looks almost exactly the same. So it's again x plus or minus, but instead of a z, you use something called t here, and you use sample standard deviation over square root of your sample size. So this t here is something that looks like our z. So z is for standard normal distribution, which is a bell curve, and t is also for a bell curve, but different type of bell curve. It's more wide and more low, but it's still a bell curve, and it's called student's distribution or t distribution. And this one is called standard normal distribution or z distribution. So just like the z table, you can find the t table in the appendix of your book or online in the internet. So just search for the t table and you will find tons of t tables. Well, what else? Yeah, usually for the same level of significance, for the same level of confidence, values for t are larger than values for z. So for example, for 95% confidence, you'll have z equal to 196, and your t will be 2.1 or 2.01 if I'm not mistaken. So it's larger, and the more confidence you get, the more will the difference between t and z be. So for 99% confidence, you need to take t 3.3 something or something like that. Or anyway, you can look it up in the table whenever you need it. So t table differs from the z table a bit. In z table, you only have values for z and the probabilities. In t table, you have your probabilities starting from 90% and all the way up to 99%, and you have your sample size or degrees of freedom. So for example, our sample size is 2, that means degrees of freedom is 1. If we take sample size of 40, then our degrees of freedom are 39, and so on. So you choose appropriate sample size or degrees of freedom, you choose your confidence level, and you get your t value. Okay, but on the other hand, they are very similar. You just have z when you know, yeah, let me just repeat that. So if you know the population standard deviation, you use sample mean plus or minus z times standard deviation over square root of sample size. If you don't know population standard deviation, then you use sample mean plus or minus t times sample standard deviation over square root of n. And that's it. So next time we will look at how we use that to test the hypothesis, to check if the data is different, and so on. But for now, that's all. So, okay, thanks, bye.